Here we go, projectiles. So by the end of today, or by the end of the notes, I guess I should say, if we don't finish them today, bless you. By the end of the notes today, you should hopefully understand what a projectile is and be able to give examples. And you should be able to understand and apply, this is the hard part, be able to apply the two big rules of projectiles. All right, so that's the deal for today. I don't know that you have to write that down. Okay. I'll wait till people write that down. The other thing I'll say to you guys is a lot of times when I write these notes up, I sort of put more text on the board than I need. Don't feel like you have to write down every word. Write down the gist of it in words that make sense to you. So when you're studying later, you understand it. Okay. Anybody still writing this? All right. So here we go. So projectile. First of all, I got to give you a definition of a projectile. Okay. So, technically speaking, a projectile is any object that's in free fall. And we just finished learning free fall, right? So we said that an object was in free fall anytime you throw it or drop it, right? Okay. So if I take the tennis ball and drop it, it's in free fall, it's a projectile. If I take the tennis ball and throw it straight up in the air, it's in free fall, so it's a projectile. If I throw it down, it's in free fall, so it's a projectile. Okay? So all of the examples of free fall we've looked at so far are projectiles. Okay? Usually, however, when you talk about a projectile, you're talking about something that's in free fall that also has horizontal motion. All right? So stop writing for 1 second in a minute. Stop writing for 1 second. So, technically this is a projectile. All right? But usually when you talk about a projectile, it has to be moving horizontally. So instead of doing this, we're going to do this. Make sense? Okay, vertically it was still, well, I'm getting that. All right. So instead of talking about this, oops, now we're going to talk about this. Oops, that was embarrassing. All right, but so notice it moved horizontally as well as vertically, right? Okay. So that's it. A projectile is an object in free fall. Usually we assume that it's also moving horizontally. So anytime you drop or throw a ball in any direction, it's a projectile until it hits the ground. So you can either write all of this down, or you can write the words. An object is a projectile anytime you throw it in any direction. So drop it. So that is the deal with what's up there in red. Are you protesting, Stephen?
Yeah, Stephen and I are not talking anymore.
I'm sorry to hear that. We need to have like a peer mediation. Is that a thing?
No, I think.
Do we have that here? Is that a thing? Peer mediation? Do you guys know what I'm talking about? No? It's a thing in some schools.
He said because it's supposed to school and I was just like, get away from me.
Get out the room. I guess I can pause. All right, so is everybody good with that? All right, so to summarize, an object is a projectile anytime you throw it in any direction, after you let go of it, and until it hits the ground. Okay? And because its velocity is changing, it's accelerating. On the way up, it slows down. On the way down, it speeds up. And the entire time, it's changing direction. Okay? Everybody good? All right. Can I click ahead, or are a couple people still writing? I'll go get the tennis ball off the floor, so I can eat it again in a minute. I had some leftover pizza I was going to bring for lunch today. My wife ate it yesterday. Curse you. So I'm stuck with the cheese pizza instead of my leftover pizza. What did it have? Bacon and pineapple and onions. I know, right? You guys are like, ew, that's really gross. Varies. Off Mama Rosa's. This was from Papa John's. Yeah, Mama Rosa's. The Mama bread, man, that's my jam. It's so good. They put the little sesame seeds on there. Genius. You don't think about it, but sesame seeds actually, they have flavor. All right, is everybody good? This is all recorded for all of eternity, too. All right. What's going on in that physics class? They're talking about pizza. All right, are we good? All right. All right, so here we go. The two big rules of projectiles. Why do you think that I made this slide so big? Because it's crazy important. If you understand the two rules of projectiles, you can solve any projectiles problem I give. All right? We just did projectiles in my AP class. I gave them the exact same notes. All right? Like, this is it. If you understand these two rules, that's it. All right? So, yes, I've used these notes also with regular physics for 19 years. So, this is the deal. All right. So, here we go. Here is big rule number one. Big rule number one says the horizontal velocity of any projectile anywhere in the universe will remain constant. Then it wouldn't be. Yes, gravity would be different, but that doesn't affect big rule number one because of physics. I don't mean that in a snarky way. When we get to Newton's laws, we'll address why this is true. I mean, you can test it on the movie. I can't answer that without teaching you more than what you know at this instant in time. So I'm not trying to be dismissive. We will get there. Big rule number two would be different depending on your location. Big rule number one, not so much. Okay, everybody good?
Yeah.
All right, so on random day at some point in the last few days, and I don't remember which day it was, we learned what horizontal velocity was. Anybody remember? We didn't talk about it real long, so I might need to review it real fast. No? Okay, so let's talk about horizontal velocity and vertical velocity. All right, so check it out. So imagine that you throw a ball. So here's you. All right, so you throw a ball off of a cliff or a building or whatever that is you're standing on there. All right, so suppose you take a photograph of the ball at the instant that the ball is right here. Everybody point for me. At that instant, which direction is the ball moving in? It's going to go in this way, right? It's moving forward and down. So the velocity is this way. So I'm going to label that with a V because that is the velocity of the ball. All right? But the idea is, at that instant, the ball is moving both horizontally and vertically, right? So if I draw a little arrow this way that extends as far to the right as my original arrow, I can label that Vx. That's my horizontal velocity. We're going to get there. Eventually it'll become a motion vector, but yes. All right, so what that horizontal velocity does is it measures how fast the ball is moving horizontally. It completely ignores the fact that the ball is moving down a little bit here, and it just focuses on how quickly is the ball moving sort of this way. Okay? And then similarly, we can talk about vertical velocity, which we would call Vy. And the vertical velocity is a measure of how quickly the ball is moving up or down. It completely ignores motion side to side. All right? If this helps any, it's this. Do you guys know on an airplane, there's a thing called an altimeter that measures the altitude of the plane at any given time? All right? That doesn't tell you anything about how far you are from Chicago. It just tells you how high above the Earth's surface is, right? So as the plane goes down, the altimeter is going to say, oh, the altitude is decreasing, right? Vy measures how quickly your altitude is decreasing. Make sense? And Vx measures how quickly you're moving horizontally from, whatever, Chicago to Denver or wherever you're flying. It's how quickly you're making progress that way. Okay? If you picture the sun being directly overhead, the shadow is going to be right under the ball, isn't it? Vx measures how quickly the shadow moves across the ground. It's just measuring how quickly the object is moving horizontally. Make sense? Questions? All right. Do I need to write out word definitions for well, I already did write out word definitions for horizontal and vertical velocity. So you've got those. But that's a quick review. Good? Questions with it? All right, great. So big rule number 1 says that horizontal velocity is constant. Vx is constant. That's big rule number 1. Cool?
What about like wind? What about when you throw something and like the wind makes?
Really good question. So what about wind? I realized a minute ago, I think I didn't emphasize this. Remember when we talk about projectiles, to be in free fall, we got to assume there's no air resistance. Okay, so yeah, that for sure would be an issue. Yeah, because if there's air resistance, then rule 1 totally falls apart. Okay, and that's a good observation. Right, so everybody got that? We are, as always, going to assume no air resistance. Okay, because it's crazy difficult to calculate the air resistance. All right, so we did this, we did that, we did this. Oh, we did that. Here we go. All right, so here's what big rule number 1 is really telling us. It's telling me that if I have a car that drives off of a cliff, so I'm going to make a drawing here. Here's my cliff, here's the ground. Let's draw ourselves a little car. Hello, I'm a happy car. All right, so our car is driving horizontally at 20 meters a second. Now, because the car is driving horizontally, I can label this 20 meters a second as my Vx, right? That's the horizontal velocity. So write that, draw that, and then we will discussify. It's not a word. All right, so we should talk about the path that the car follows after it goes off the cliff. So is the car going to do this? Oh no! Like Wile E. Coyote? No. Is the car going to just make a beeline and go in a straight line and hit the ground? No. The car is going to follow a path that is shaped like a parabola. It is part of a parabola. If you didn't know that, that's fine, but you, at the very least, knew that it was probably curved, right? Does that make sense? Because the car is moving horizontally and then, right? All right. Now, let's suppose, where is my black pen? Here it is. Suppose the car takes 4 seconds to hit the ground. Right? So what big rule number 2 is telling me is that the entire time my car is in the air, it's going to move horizontally 20 meters every second. So 20 meters, 20 meters, 20 meters, 20 meters. How far is it going to go in 4 seconds? 80 meters, right? So that means that this distance down here is 80 meters, right? All right, so let's do this. Let's break it up into 4 equal chunks. So I'm going to chop it in half. That's 2 equal chunks. 4 equal chunks, right? Okay. So here's what I'm going to do. Dotted line. T equals 1. That's where the car is after 1 second. T equals 2 seconds. That's the last time you have to hear me do that. T equals 3 seconds. T equals 4 seconds. All right. And during each of those 1 second intervals, how far did the car go? 20 meters. So that means that each of these dotted lines are 20 meters apart. So every second that the car is in the air, it moves horizontally 20 meters. Make sense? That is what that rule is telling us. As a quick side note, we'll talk about this in a minute, but notice vertically, does the distance seem like it's constant vertically? No. In the first second, it only fell a little bit. Next second, it fell further. Next second, further. Last second, holy cow. Right? Okay, but the entire time that it's moving, it is moving horizontally 20 meters a second. Cool? Please don't, when you draw the path that the projectile's following, don't do this. Okay, it's got to be more of a parabola. It's got to be always moving forward. It's never straight down. You know what I mean? All right. Any questions with that? All right, so now I need to prove this to you. So I don't know if I can prove it, but I can certainly do a couple demonstrations that will help you appreciate that that is true. All right, so if you're watching the video, I apologize. You're just going to get audio on this. Somewhere in a tennis ball. Where did I put it? It's right here. Okay, so here we go. I know, right? Hope I don't die. All right, so here we go. I'm standing on a skateboard, right? I'm holding a tennis ball. All right? Right now, is the tennis ball a projectile? No, because there are two forces on it. Gravity's pulling it down, I'm holding it up, right? Okay? Okay, so check it out. I'm going to throw the ball up. Projectile, right? Did it move horizontally at all? No. So in that example, the horizontal velocity was 0. It didn't move horizontally at all. But when I threw it, I gave it vertical velocity. Yes? Okay? So that's that. All right, now, example number 2. The ball is moving horizontally, yes? More or less at a constant velocity, right? It's not perfect, but the idea is that as I roll on the skateboard, there's really nothing impeding my motion. So more or less, I roll at a constant velocity, right? It's not perfect because friction is going to slow me down a little bit, but not too bad because they're good skateboard wheels. And there's a little bit of air resistance that's going to slow me down, right? So more or less, the entire time that I'm rolling, the horizontal velocity of me, the skateboard, and the tennis ball are all more or less constant. Yes? Good. So, just so that we have some numbers to talk about, let's suppose that I'm rolling that way at 2 meters per second. Okay, it's probably not that fast, but whatever. So let's suppose I'm rolling that way at 2 meters a second. Okay? So what that means is the entire time that I'm rolling, the tennis ball is moving that way at 2 meters a second. All right? So what I'm going to do now is I'm going to combine the two types of motion. All right? So I'm going to push the ball up while I'm rolling. So I'm going to be rolling horizontally at 2 meters a second. When I throw the ball up in the air, am I doing anything to take away that horizontal motion? No, all I'm doing is pushing it vertically to change the vertical motion. Hey Maria, how are you? Good, thanks. You have a pass for me. Did you bring me coffee?
No, it's lemon.
Did you bring me lemon water? Okay, so I'm going to move this way 2 meters a second. I'm going to push it, give it vertical velocity. Watch what happens. Are you ready? Here we go. Right? I caught it, right? It's the exact same thing as if I hadn't been moving. Look. The ball's moving horizontally. It's still moving horizontally. Okay? Me throwing the ball did not change its horizontal velocity. Does that make sense? So, the entire time the ball is in the air, it's moving horizontally 2 meters per second. Make sense? It's exactly. I can't take more. I don't think I ever could, to be honest. I tried really hard. Yeah.
Did you skate back for that?
A long time ago. All right. So here's what we just saw. All right. So the skateboard was moving horizontally at 2 meters a second, right? So at the instant that I threw the tennis ball, two things were happening. One, it was moving horizontally at 2 meters a second, and it was moving vertically at whatever, some number, 3 meters a second. So at the instant that I released it, the tennis ball was actually moving this way. Did you guys see me throw it at an angle? No. So, but think about what happened. The idea is, at the instant that I threw it, remember we talked about the ant going across the conveyor belt? Right? The conveyor belt's going this way, ant's walking that way, so the ball, or the ant goes this way, right? Same idea. Skateboard's moving this way, I'm throwing it this way, I'm actually throwing it this way. Thank you for catching that. Good? All right. Relative to me, the ball literally just went up and came down. Relative to you, the ball went up and came down. Right? So it's equivalent to me throwing it like that, right? At an angle. I don't know why it said this. But are we good? So, then what happened is the tennis ball went and landed over here, and at that instant, there's me, right? Because both me and the ball were moving this way at 2 meters a second, right? So, if after 1 second the ball was here, the skateboard was right under it. If after 2 seconds the ball was right here, skateball was right under it. If after 3 seconds, skateboard. 4 seconds, skateboard. Make sense? Because both the ball and the skateboard are moving 2 meters horizontally every second. So that's a crappy drawing, but these are supposed to be 2 meters every second. Good? Questions? Is that a question, Jacob, or just a sleeve adjust? All right, is anybody unhappy about what we've discussed? All right, here we go. Kabam! Write it down. Answer the question.
The Ohio State University.
No, we have not done big rule of 2 yet. I'm going very slow. Okay, we're almost done, guys.
This is another example for rule number
This is another example of big rule number 1. So the question says, suppose a plane is flying horizontally at a constant velocity. So here's my airplane. You look like a ghost. Take that. All right, so here's the package, right? Doors open up. All right, so 200 meters a second, that's the velocity of the airplane. How fast is the package moving? 200 meters a second. So every second that the airplane is moving, it's going to go 200 meters. So when the airplane opens up the doors, the package is going to fall, right? Okay? So here's the ground. In the time it takes for the package to fall, the airplane is going to move forward, right? Yeah, nobody can draw airplanes as well as me, so you're just going to have to come to grips with the fact that your airplane's going to be, well, ugly. Sorry. I thought that was funnier than you guys did. All right. So my question for you is this. The airplane's going to keep moving, right? Right? When the package lands, where is the airplane? Will the airplane be in front of the package, behind the package, or directly above the package?
Thank you. No, it'll be the
Do you want to know the cheat way of drawing an airplane?
Yeah.
Airplane.
Okay, I'm gonna do that.
Gotta make it way long.
When I was in 2nd grade, that's how I drew them, and I thought they were cool. It looked like rocket chips, and you could put flames coming out the back.
I look like a dolphin.
All right. So anyway, so the idea is, as the package falls, it's also moving horizontally. At what rate? Same rate as the plane, 200 meters a second. So the package is going to go. So when the airplane gets to here, the package is here. When the airplane gets to here, the package is here. Airplane, package. Airplane, package. Because both the package and the plane are moving horizontally at 200 meters per second. Oops, I'm gonna. So let me show you that while you write, or after you're done writing. What assumption am I making again? An important one.
No air resistance.
No air resistance. Right? Why don't I have to worry about air resistance? Because it's too much calculations, and that's the assumption we make when we talk about projectiles. It doesn't matter. You know what might actually matter here is the fact that the Earth is round. The fact that the Earth is moving should not matter. But all good questions. All right, everybody got this written down? All right, I'm going to show you two videos that'll help you appreciate this a little bit better. Everybody's done writing? Yes?
Isn't that like a longer path too? For like,
Isn't it a longer path? Yes. So, you guys, we have an awesome question here that you need to hear. Jack just said, listen, girls. Jack just said, isn't it a longer path for the package to follow? And the answer is yes. Why does that weird you out?
like, it's like moving the magnet 20 feet forward, so it could take shorter, like a shorter time for using that swap in the package.
Okay, so what Jack is thinking, well, they're both going 200 meters a second. So the package should take longer because it's got farther to go, right? Okay, but please hear me say this. I'm not saying that the package is going 200 meters a second. I'm saying that the package is going horizontally 200 meters a second. All right? As it falls, doesn't gravity make it go faster? So overall, it speeds up as it falls, and we'll see that when we get to rule number 2 in a minute. Okay? So it is speeding up. It's just not speeding up horizontally. Okay? So if you ignore the vertical motion, both objects are going to go horizontally the same distance in the same time because they have the same horizontal velocity. Make sense? We'll deal with the vertical velocity tomorrow when we get to big rule number 2. All right. Are there any questions? All right. So here's a video which will illustrate it. The first one doesn't work quite as well, but I'm going to show it to you anyway. Oh no, I did it twice. All right. Watch. So, airplane, it's going to drop some sort of package or something. Watch what the package does. I don't know what they are. All right. So, did you guys see what they did? Yep.
I'm sorry.
How do you know exactly when it drops? No.
Yeah, go home.
You don't have it.
Watch it again.
Mr. Hecker, I just got it in college.
Congratulations. That's amazing.
Okay, watch the video.
Yeah, congratulations. You learned physics. Who cares about college? Okay, yeah, look.
Oh God.
So,
Sorry.
I know, it's super exciting and way more important than physics and physics. So the idea is, whoa, that was not what I wanted to happen. The airplane is moving horizontally at some velocity, right? So are the bombs or whatever these things under it. And so, look, they're all right under it, right? So this one here did this. That's not going to help any. All right, anyway, they're both moving horizontally at the same rate. The other video, I think, makes it a little bit clearer, so let me show you that. All right, this one's better. I don't know why I didn't just show this one. All right, so what you can see here is the airplane is flying this way. You sort of can't tell that the airplane is flying because whatever's filming it is moving with it, but I mean, it's got to be moving, right? Otherwise it wouldn't be flying, right? So it's moving horizontally at some velocity. So are the bombs that are under it, right? So what I want you to understand is that at this instant, why does it keep doing that to me? At that instant, this bomb right here is moving both horizontally and vertically, so it's actually moving at an angle. All right? In a minute, it changes camera angles and it shows you from a stationary camera what the bombs are doing as they hit the ground. So watch.
Delivering cruise missiles and other smart weapons. During deserts.
All right. So if you watch, I'll rewind it in a second. But if you watch one of the bombs are going at an angle like this because they're moving horizontally from the plane's motion, and vertically because of gravity. All right. Check it out. Oh no! What'd I do? How do I? Stupid technology.
We use permission for volume, not precision is required.
So watch when they hit the ground.
Of delivering cruise missiles and other smart weapons.
Can you see them?
Storm.
Look. Right?
So why don't they all just fall, like, figure that, so, you can drop, like the first video, they all drop in front of each other. Why did that happen?
I don't know why they didn't use signals.
Yeah, they're being released. Yeah, if you're asking what I think you are, that's the right answer. But yeah, so when the plane is here, it drops one, right? That one falls. Then it drops another one. That one is moved forward, and the next one comes out. You know, so it's just this. Good? Questions on this? All right. So,
Of the tonnage of the weapons dropped by coalition forces.
all right. Projectiles notes. All right. So we're all good with this, yes? All right. Write down big rule number 2. We're not going to get too far with it, but let me at least introduce it to you, and that'll buy us a little more time tomorrow. I was hoping to get through both rules today, but it always takes longer than I think it does. All right. So notice, big rule number 2. So big rule 1, horizontal velocity is constant. Big rule 2 is about the vertical velocity. And it tells us that vertically you have an acceleration of -10. Why should this number look familiar to you guys? That's the acceleration of gravity, right? So, Spencer, you asked before about other planets. On the moon, the acceleration of gravity is only 1.6. So, on the moon, this number is 1.6. On Jupiter, it would be -25. On Mercury, it would be negative, I think it's 8.3, or maybe that's Mars.
How do we calculate that?
We will learn that when we do Newton's universal law of gravitation, or law of universal gravitation. So we'll get there.
Isn't like the idea of gravity like way different?
Yes, it is very different. So we will talk about that towards the end of the year. And Newton's idea gives you accurate results for large enough bodies. All right. So here is the question that we're going to answer tomorrow. I'm not going to answer it now, but let me at least set you up so you can think about it tonight. Maybe you'll lose sleep over it. So suppose you've got 5 cars that drive off of a cliff. All right? It's all the same cliff. They all drive off the cliff at the exact same time. The question is, which one hits the ground? Well, we still have 5 minutes, don't we? Yeah, I was thinking we get it at 41. Oh, we have 5 minutes. Let's do this. I know. No homework, so unless you didn't finish yesterday's homework, in which case you do have homework. All right, so let's do this. So we got these 5 cars that are going to drive off of a cliff. The cliff is 5 meters tall. They're all going to go off at the same time. So the question is, which one hits the ground first? All right. Now, there's a reason that I chose 5 meters. When we did free fall, one of the things that we learned was that if you drop an object from rest in 1 second, an object falls 5 meters, right? Remember we decided, everybody's like, oh, it falls 10 meters. It falls 5 meters, right? So remember it had to take time to speed up. Okay. So it's going to take, in 1 second, an object dropped from rest will fall 5 meters. All right, so I'm going to add a car F. So imagine we've got a car F, and it's just going to be dropped off the cliff. All right, so here's a crane. He's mean. All right, here's the crane. He's going to drop a car. The car is going to fall. So if the cliff is, in fact, 5 meters tall, we just decided that it would take 1 second to hit the ground, right? Everybody good? Now, rule number 2 tells us that all objects fall down at negative 10 meters a second squared, even if they're moving horizontally.
Well, crap.
So theoretically, they should all hit the ground at the same time. The only difference is car A is going 2 meters a second. But point for me, what direction is it going 2 meters a second at? It's going 2 meters a second this way. So car A is going this way at 2 meters a second. So it's going to go, right? It still takes a second to fall, but during that 1 second, it's going to move horizontally 2 meters. Okay? Car B is going faster. It's going 10 meters a second. So it's going to, in the 1 second that it takes to fall, it's going to go horizontally 10 meters. So it's going to go and land 10 meters away. All right? The idea is this. All the cars here begin with a Vx, right? They've all got a horizontal velocity. Yes? But look, this is a dumb question. You ready? I'm going to walk this way at 2 meters a second. I'm walking this way at 2 meters a second. How quickly am I moving up? I'm not. How quickly am I moving down? I'm not. Right? I'm just moving horizontally. What's my vertical velocity? Vertical velocity. 0. Right? I've got horizontal velocity because I'm moving horizontally, but I'm not moving up or down at all. All right? So the idea is, because all of my objects begin vertically, they all begin from rest, they all fall down in 1 second. All right? I will prove that to you tomorrow.
Right here.